We're going to take a look at a couple of simple sorts. It's brute force, basically looking at every single element. If we're to sort a list of elements, recall that sorting is a process of converting a list of elements into either ascending or descending order. You may have carry out sorting when, let's say, arranging papers in alphabetical order or arranging envelopes to have ascending or descending zip codes. There are three simple sorts out there. The first one is selection sort. We went through this briefly in earlier chapters. There's also bubble sort and insertion sort. So these are the three unsophisticated brute force approaches. They are not efficient at all, but they're easy to understand and implement. For this lecture, we're going to look at selection sort from algorithmic approach standpoint and also visual standpoint. Selection sort is a sorting algorithm that treats the inputs as two parts, a sorted part and unsorted part. So this is just an illustration how you would do it initially. Let's say if you have original list, and just say this is original. You have this new list. This new list in the beginning is all blank. You don't have anything here. You will go through the original list and look for the smallest one. Let's just say from original to new, this selection sort sorts the entire list of elements in ascending order. You find the smallest one first, looking at this one. So the very first comparison is one against the other, O of n. So that's the smallest one. Then you cross out the elements. The element has been moved. So now you have n minus 2 elements that you have to look at. N minus 2 O of n minus 2 is going to give you O of n. Let's say second smallest one is here, and you cross it out, and you move them over here. The second one, you don't want to look again. This whole process repeats the essence of selection sort until you're done. This new list is going to take up some memory. Let's say if the original list is O of n, the newer list is going to get you another O of n. This is a good approach, but it's not the best approach because it's memory consuming. So that's basically what this sorting algorithm is. Going through this list, looking for the smallest one. This is using a string lexicographical comparison. H has the smallest order of all of the other string instances. McCarthy, M, and then so on and so forth. This is the two-list approach. You can also forget about having this list at all and see if you can just rearrange elements inside this original list. That would save you some memory. Let's look at doing this swap in place. So the improvement here is using original list and exchanging with the name on the original sheet. Instead of having a different sheet, O of 1 in terms of memory, but time-wise, it's still pretty bad. It's going through every single one of the elements, looking for the smallest one, cross it out, do the second one. That's really the essence of this, the selection algorithms. It's from current going to size minus 2. Array indexing starts with 0. So your very last element is the size minus 2. Let's say if you're here. So the current is basically all the way through size minus 2. So there is size minus 1 element, but the very last one that you have to look at is size minus 2. You're doing a pairwise comparisons there. Across the entire list of elements, you do a swap, swapping the smallest one against the current. So swapping Wilkes against McCarthy. Let's look at the diagram here. Initially, you start out with the index 0 at the very top, 126. This 126 is being compared against the rest of it. This orange is my outer loop. You have the red one, which is my inner loop. This inner loop goes from whatever the outer loop current is, current plus 1, checking to see if every single element inside the second loop is smaller than 126. If this is yes, keep going. While you keep going in the inner loop, make sure that you have the smallest that you can keep track of. This index 3 elements 1 is the smallest one. When this is found, you would do a swap. This 126 was 1. 126 used to be at 0, and now it's at index 3. So there's a swap right here, which is in the middle part. This is the swapping. Now we know swapping is O of 1 times, maybe 3 or 4. The swapping is pretty fast. But what is not fast is the inner loop in red. What you're doing is you have to go through size minus 2 elements, starting from the second element down. Your outer loop in orange is going to move down to index 1. So the third one, the outer loop going at 2, so on and so forth. This outer loop in orange runs from the very top all the way to size minus 2. You don't have to compare the last one. The last one itself basically goes through size minus 2. 3 is your last one. Your inner loop in red continues to move down, bypassing 43 because 43 is the outer loop. Comparing 43 against the rest of it, 22 is less than 42, yes. What about 126? This one is no, this one is no. And then doing a swap, you move on to the third one. The outer loop again goes on into the next one and then do the comparisons. If there is none, then don't move it. If there is yes, keep track of the smallest yes. So this is the selection sort algorithms that treats the input as two parts, a sorted part and an unsorted part. So the sorted part is right here, and the unsorted part is here. This is a sorted part, and this is an unsorted part. The selection sort algorithm runtime is actually O of n squared. You have an outer loop that goes down O of n. What about the inner part? If the list has n elements, the outer loop executes n minus 1 time. For each of those n minus 1 outer loop executions, the inner loop executes on average n divided by 2, n half time. Why is that? The inner loop we're looking at here is in red. This one is n minus 1. And what about second one? N minus 2. Third one, n minus 3, so on and so forth. So number of inner loop that you have here is 1 plus 2 plus all the way to n minus 2 plus n minus 1. If you add them all up, this is going to give you n minus 2 on average. Outer loop is n minus 1, inner loop is n divided by 2. The total is n minus 1 times n divided by 2. What is n minus 1 times n over 2? O of n squared. This is quadratic time for selection sort algorithm. You have a sorted part and an unsorted part. The current basically keeps track of these things from 0 indexing to size minus 1, but the actual comparison from the outer loop is actually size minus